So in this video, we're going to take our Lego workshop example and represent it using those 4 different components of a linear program. For this video, we're going to actually do 3 of those 4 components and represent an entire model. And then in the next video, I'm actually going to take that and represent parameters and sets so that we can more concisely represent a mathematical model. But first, let's get started. We have this Lego workshop example, so you can pause and read this here if you haven't already gone through this. But essentially, we're making teas and we're making cakes, and we have a certain amount of Lego material, small bricks, big bricks, and tea demand, and we must determine how many teas and cakes to make. And so what we're going to do is take this and represent it using decision variables, objective function, and constraints. So first here we have our decision variables. And so what we're needing to tell Matthew is how many teas and how many cakes to make. So first and foremost, this is our first component here. And so we're going to represent it using x1 and say is equal to the number of teas to produce. Just make that nice towards the end. Okay. And so writing x1 equals the number of teas would be just slightly imprecise. We need to know an action associated with that. It is the number of teas he should produce. It's not the teas he should buy. It's not the teas of something else. It's the teas that he should produce. And then we also have x2 is the number of cakes to produce. And so here we use the x1, x2 rather than, let's say, a T and a C to represent teas and cakes, because we could scale this up very nicely and use in shorthand where we could say x sub j is equal to the number of item j to produce. In our particular case, j takes on the values 1 and 2. So now we have our decision variables. Second, we're going to work through our objective function. Okay, objective function, what's our goal? What's our motivation? For our particular problem, we're trying to maximize our profits or revenue there. And so objective function always has a min or a max, and so our particular problem is max. We know we make revenue $3 per tea produced, and so we know x1 is our number of teas produced, and so we're going to maximize 3x1. We also get money for cakes produced, so we get $2 per cake produced. x2 is our number of cakes produced, and so this is plus 2x2. Okay, there's our objective function. Next is going to be our constraints. Our constraints are going to use data, but they're going to impose some limitation to the action. So we have data associated with small bricks. And so we could shorthand say we have a small bricks constraint. But really what we're saying with the small bricks constraint is saying the number of small bricks that we use is less than or equal to the number of small bricks we have available. So I'm just going to write that in words. Our number of, I'm going to shorthand, do SB, small bricks. The number of small bricks used has to be less than or equal to our number of small bricks available. We have the same thing, but for big bricks. So number of big bricks, I'm going to shorthand BB, used is less than the number of big bricks available. This is different than saying we have 10 small bricks, we have 8 big bricks. We're imposing some limitation or constraint on our action. We also have a constraint that says the number of T's produced has to be less than or equal to our T demand. And then one thing to just never forget here is that we should have non-negativity associated with our decision variables. So I've written out this in words. In reality, when you're going to model and you become refined and have practiced enough, you're not going to necessarily write out these 4 different constraints in words. You're going to write them out mathematically. So what I'm going to do here is I'm going to write it mathematically. So let's take this first one here. Our number of small bricks used. Okay, we use small bricks for teas and cakes. We use 2 small bricks per tea and 1 small brick per cake. And we know, going back up here, x1 and x2 are our number of teas and cakes. So to represent this first one, we know that 2 times x1 plus x2 has to be less than or equal to 10. That's our first constraint. We also have a constraint for big bricks. So we think number of big bricks used. Okay, we have 1 per tea, 1 per cake. So that's going to be x1 plus x2. And we have 8 big bricks available. Then we say our number of teas produced has to be less than or equal to T demand. Well, our number of teas produced is x1. Our T demand is 4, so we have x1 is less than or equal to 4. Lastly, we have non-negativity, which you would typically write x1, comma, x2 is greater than or equal to 0. Putting this all together, we're going to get our first model where we are maximizing, let me just scroll up here, maximizing 3x1 plus 2x2 subject to, so ST is subject to, 2x1 plus x2 is less than or equal to 10, x1 plus x2 is less than or equal to 8, and x1 less than or equal to 4, and then lastly, we have non-negativity. To make it easy to reference these, I'm going to add in some equation numbers. I'm going to call this equation 1, 2, 3, 4, 5. Okay? And so typically associated with a model is a description that describes the model. So this isn't one of our 4 components of a linear program. This here is our linear program. But to aid in the understanding of this linear program, there's often a description. So you could see associated with this something like this. We could say in objective 1, we maximize revenue. Then you can say in constraints, I'm actually going to merge constraints 2 and 3 because fundamentally they are doing the same thing. We're saying the amount of a resource used, small bricks or big bricks, is less than or equal to the amount of the resource available. So I'm going to say in constraints 2 and 3, we limit the amount of, I'll just generalize, bricks used by the number of bricks available. Okay. Then in constraint 4, we're saying the amount of an item produced has to be less than or equal to the demand. So I can write that here. In constraint 4, we limit the number of teas produced by its demand. And then lastly, I'll just scroll up. Constraint 5 is non-negativity. And so I'm going to say in constraint 5, we restrict the decision variables to be non-negative. And so with that, we have our first model. This is our linear programming model. In order to do this, we need to represent our decision variables here, x1 and x2. And essentially our model is this combination of objective and constraints. As we get better, we're going to skip this objective function and constraints, and we're going to go straight to this model here. And then to convey what this means, we have a description associated with this model.